In this session, we look at conditional and cumulative conditional PDFs. We didn't have a chance to do this during the semester, actually, but we can, for the sake of completeness, cover it. So we've already done conditional PMFs, right, for discrete random variables, and we would now like to do conditional PDFs for continuous random variables. Again, and the results that we will see are analogous. Okay, so this is how you define a conditional PDF. You see it's the same as the definition for the conditional PMF. The conditional for x given y is equal to the joint for x and y divided by the marginal for y, provided that the point at which you're evaluating the marginal doesn't give you a zero value. Okay. And again, as before, we have a multiplication rule. The joint PDF for x and y is equal to the conditional for x given y times the marginal for y. Okay. As before, again, we're talking about probabilities. So the conditional for x and y, evaluated anywhere, is greater than or equal to 0. These conditional probabilities have to lie between 0 and 1. And the way to find the probability that x lies between a and b, given that y is equal to y, is given by integrating the conditional for x given y from x equals a to x equals b. In the PMF, in the case of the conditional PMF, it was a sum. Right now we're doing continuous random variables, so it's an integral. Okay, so let's do an example. I'm going to give you the joint PMF, and we're going to find the conditional PMF. Right? So supposing x and y are continuous random variables with a joint PDF f sub xy, which is of the form f sub xy is equal to 6/5 x plus y squared for x and y in the unit square and 0 otherwise. Okay, and given this joint PDF, I want to find the conditional PDF for x given y. Okay, so one way to do it would be to say, well, the conditional for x given y is the joint for x and y divided by the marginal for y. So we could find the marginal PDF by integrating the joint PDF. You integrate out the x, and then you'll be left with the marginal for y. Okay. So we're going to find the marginal PDF for y. And so to do that, you integrate the joint PDF, and in principle, you integrate out the x, so x would go from minus infinity to infinity, but we're going to only consider the points where this would not be 0, and that's where x and y are both in the unit square. So assuming that x and y are in the unit square, so y is, right, x varies between 0 and 1. So you integrate from 0 to 1, the PDF, the joint PDF, then in the unit square has the form 6/5 x plus y squared dx. And if you do the integral and then you remember you're keeping y to be some fixed value in this case. You're integrating from 0 to 1, y is fixed, and then when you evaluate, you calculate the antiderivative, and then you evaluate at 0 and at 1, you'll get 6/5 times 1/2 plus y squared. Okay, so inside the unit square, right, outside the unit square, this conditional PDF should be set equal to 0. Inside the unit square, the conditional for x given y is the joint for x and y divided by the marginal for y, and that's equal to, so inside the square, this joint PDF is of the form x plus y squared. So it's of the form 6/5 times x plus y squared, sorry. 6/5 times x plus y squared over 1/2 plus y squared, and 0 outside the unit square. Okay. Base term, as in the case of the conditional PMF, same for the conditional PDF. The conditional PDF for x given y is defined to be the joint for x and y divided by the marginal for y, and that's equal to, we now use the multiplication rule for the numerator. It's the conditional for y given x times the marginal for x. Okay, so sometimes the conditional for x given y might be more difficult to find than the conditional for y given x. So in such a case, you might want to use Bayes' rule, Bayes' term, this way to evaluate it. Okay. Similarly, by symmetry, the conditional for y given x is equal to the conditional for x given y times the marginal for y divided by the marginal for x. Law of total probability. You can find the marginals from the joint PDF, right, for x and y. So the marginal for x can be found from the joint PDF for x and y by integrating out y from -infinity to +infinity. Now, if we use that multiplication rule, this is the same as integrating y from -infinity to infinity, and the integrand is the marginal for x given y times the marginal for y. Similarly for y, if you want to find the marginal from y from the joint PDF for x and y, then you integrate x from -infinity to infinity. And now you can replace this integrand, which is the joint PDF, using the multiplication rule. You can replace that by the conditional for y given x times the conditional times the marginal for x. Now, in the case of, again, as we had for conditional PMFs, for conditional PDFs, if it turns out that x, in the special case where x and y are statistically independent, then we have that the conditional for x given y is the same as the marginal for x, and the conditional for y given x is the same as the marginal PDF for y. And in the discrete case, we had a conditional expectation, and that was given by a sum. And in this case, it would be, in the continuous case, it would be given by an integral. So if we've got continuous x and y, the expectation of x given y is defined as the integral from -infinity the integral over x from minus infinity to infinity of x times the conditional for x given y. Okay, so as an example, let's say we had the joint distribution for x and y given as it has the form 21 over 4 times x squared y in the region which is defined by x squared less than or equal to y less than or equal to 1. And it's 0 elsewhere. Now, if we wanted to find the conditional Pdf, okay, for y given x, what would you do? Well, the conditional for y given x is the joint divided the joint Pdf for x and y divided by the marginal Pdf for x. So how would you find that? You would integrate out the y on this region. Basically, everywhere else is 0, so you would integrate from y equals 1 to x squared. Well, sorry, from x squared to 1. Okay. And that would leave you with the marginal for x. So once you have the marginal for x, you can find the conditional Pdf, and you should get that the conditional Pdf is given by 2y over 1 minus x to the fourth on the region defined by x squared less than equal to y less than equal to 1. Okay, so now once you have, and now to get the conditional expectation for y given x, you would multiply this by y, and you would integrate over the region where the Pdf is not equal to 0. So that's from x squared to 1. So y times the conditional that we found, integrate that from x squared to 1. X is being held constant here, right? It's for y given x. So we can pull out any function of x outside, right? And then if we do the integration, we get 2/3 of 1 minus x to the 6th divided by 1 minus x to the 4th. Two examples of finding conditional expectations. Now, for PMFs and PDFs, before we had related cumulative mass functions and cumulative distribution functions. If our PMFs and PDFs are now conditional PMFs and conditional PDFs, then we can also talk about cumulative conditional PMFs and PDFs. Okay, so this is how we define them. The cumulative for discrete x and y, the cumulative conditional PMF for x given y, evaluated a and b, is equal to the probability that x is less than or equal to a, given that y is equal to b. And you find it by summing over all the x's less than or equal to a. You sum the conditional Pdf for x given y, evaluated at x with y equal to b. Okay, so here's an example. We have two fair die. One is red, the second one is blue. You do one roll of the dice, right? So you throw both dice. X is the result from the two rolls, the sum of the two rolls, and y is the result only of the red die. So this notation, the cumulative PMF for x given y, evaluated at 7, 4. This should be a straight line here, not a comma. Okay, for 7 given 4. What does that mean? That's the probability that x is less than or equal to 7, given that y is equal to 4. Okay, if y is already 4, then what could x be? Well, y being 4 means what? Y means it's the result of the red die. So that's the probability that the blue die is equal to 1. The blue die gave 2, or the blue die gave 3. Okay. So these are 3 possibilities out of 6 for the blue die. So that's equal to 1/2. Okay, so for continuous random variables, right, you don't have the sum, you have the integral. So the cumulative conditional CDF for x given y, evaluated at a and b, is a probability that x is less than or equal to a, given that y is equal to b. That's given by integrating from minus infinity to a the conditional PDF of at t with y equal x equals t at y equals b, fixing y equals b dt. Okay. So here's a problem. We have a joint mass with probability density function for x and y, which has the form x exponential of minus x times y plus 1 for x greater than 0 and y greater than 0, and it's 0 otherwise. So the problem is to find the conditional density, the conditional PDF of x, when given that y is some fixed value small y, and the conditional density of y given x is equal to some value small x. Okay, so how do we find conditionals, right? Well, we take the joint PDF and we divide it by the marginal for x, right? Or we divide it by the marginal for y, and that will give us the conditional PDFs. So to get the marginal for x, you take the joint for x and y, and you integrate out the y. That will leave you with the marginal for x. So we integrate from, when you're integrating from minus infinity to 0, you're just integrating zeros, so we don't worry about that part. We only need to integrate from 0 to infinity. And when you on the integral from 0 to infinity, then the joint PMF has this form: x exponential minus x, y plus 1. Integrate out the y. That will leave you only with the marginal for x. Okay. That turns out to be equal to the exponential minus x. Now, same for y. To get the marginal for y from the joint PDF for x and y, integrate out the x. So integrate from minus infinity to infinity, the joint PDF for x and y dx. Okay, so we don't bother with the part that's 0, and the part that isn't 0, we integrate from x equals 0 to x equals infinity. The PDF has the form x exponential minus x, y plus 1. You integrate with respect to x. and you will get y squared plus 1. And you're assuming that y is greater than 0, so that you were integrating on the part where the joint PDF is not 0. Okay. How do you find the conditional for x given y? Well, you take the joint PDF for x and y, and you divide by the marginal for y. So we take the joint PDF and we divide by the marginal for y, and that gives you the conditional for x given y. And you're assuming that you're doing this in the area where the PDFs, oh no, it's 0. Okay. Now, if you want the other conditional the other way, the conditional for y given x, then you take the joint PDF and you divide by the marginal distribution for x, and this is the numerator is the joint this PDF, and this is the marginal distribution that we found, and you get x times the exponential minus xy. Okay, so we found the conditional distributions. Another problem would be find the distribution function for z equals x times y. And one way to do that is to find the cumulative distribution first. And once you found the cumulative distributions, then you can work out the. Once you found the CDF, you can work out the PDFs. Okay, so we take the f sub z of a, the cumulative distribution for z given for z evaluated at a, is the probability that z is less than or equal to a, and z is equal to x times y. If xy is less than a, then y is less than a over x. And so we need to integrate the joint distribution for x and y over the region where y is less than a over x. Okay. Then the probability for y being less than a over x is given by integrating from y equals 0 to y equals a over x, and into dy, the PDF dy, and then integrating over all x from 0 to infinity. Okay, so if you do that, you get 1 minus exponential minus a, assuming that a is greater than 0. Then the PDF, the PDF given by f sub z of a, so that's the PDF for a, the PDF for z, sorry, evaluated at a, is the derivative with respect to a of the CDF evaluated at a, and that's equal to minus a for a greater than 0. Another problem. Supposing that x and y have a joint PDF f sub xy, and it takes the form x squared plus 1/3 xy, and that's on the rectangle in which x runs from 0 to 1 and y runs from 0 to 2. Otherwise, it takes value 0. So the question is, find the probability that x is bigger than 1/2, given that y is greater than 1/2. Okay, so let's write this out a little bit. The probability that x is greater than 1/2, given that y is greater than 1/2, is a probability that x is greater than 1/2 and y is greater than 1/2, divided by the probability that y is greater than 1/2. Okay. Now, from the definition of the joint PDF for x and y, We know that x varies between 0 and 1, and y varies between 0 and 2. And so to find x greater than 1/2 and y greater than 1/2, we need to integrate over that rectangle where x goes between 1/2 and 1, and y goes between 1/2 and 2. Right, y is greater than 1/2, x greater than 1/2. There's no point in integrating beyond this range because then the joint PDF drops to 0. So the probability that x is greater than 1/2 and y is greater than 1/2 equals the integral over the region R, the pmfs, and then that's a double integral. So you do y equals 1/2 to y equals 2. You integrate the PDF with respect to y. Once you've done that, then you integrate with respect to x from x equals 1/2 to x equals 1, and you get 43/64. Okay, we also need probability of y greater than 1/2, and we already had that. We already found. So for that, we need the marginal PDF for y. So you integrate your PMF. You integrate the joint PDF with respect to x. You integrate out the x. You're left with the marginal for y. So that's in over the region where it's not 0. That's the integral from x equals 0 to x equals 1, x squared plus 1/3 xy dx. So keeping y fixed, do the integration, get 1/3 plus 1/6 y. Now, once you have the marginal and you want the probability that y is greater than 1/2, then integrate from y equals 1/2 to infinity, but you don't have to go all the way out to infinity because the PDF drops to 0 past 2. So you just do the integration from y equals 1/2 to y equals 2 with respect to y of the marginal PDF for y. And you take this result that we just had and that for the marginal, and then that gives you 13/16. Okay, so now feeding in all those numbers, the numerator was 43/64, the denominator was 13/16, and that's equal to 43/52. Okay, let's do another problem where where x and y are discrete now. So x can take values 0, 1, and 2, y takes values 0 and 1. So the PMF for x and y is given by 1/3 if x equals 1 and y equals 1, 1/3 if x equals 2 and y equals 0, 1/3 if x equals 0 and y equals 0, and it's 0 otherwise. Okay, and the problem is to compute the conditional for x given y is equal to 0. Okay, so by definition, the conditional for x given y is the joint for x and y divided by the marginal for y. And here y is equal to 0, so the conditional for x given y, when y is set equal to 0, is the joint PMF evaluated at x0 divided by the marginal PMF evaluated at 0. Okay, to find the marginal for y, for in the discrete case, you sum out the x, right? So the marginal for y evaluated at 0 is the joint evaluated at 0, 0, plus the joint evaluated at 1, 0, plus the joint evaluated at 2, 0. That's 1/3 plus 0 plus 1/3, which is 2/3. And then once you found that, then the conditional for x and y at x equals 0, y equals 0, you take your joint and you divide by your marginal. That's 1/3 over 2/3 is 1/2. Now for the conditional for x given y is equal to 0, evaluated when x is equal to 1, that's the joint at 1, 0 divided by the marginal at 0. At 0 over 2/3 is 0. And the marginal for x given y when x is equal to 2 and y equals 0 is the joint evaluated at 2, 0 divided by the marginal at 0. That's equal to 1/3 divided by 2/3, which is 1/2. And then that's summed up in this definition. The marginal for x given y at x when y is equal to 0 is 1/2 for x equals 0 and 1/2 for x is equal to 2, and it's 0 otherwise. Okay, so that covers the that covers the conditional PDFs and conditional expectation in the continuous case, and the conditional cumulative PDFs and Vmfs.